So just as a quick recap, what kind of models did we see so far? Well, we have the simple and multiple linear model. It's just a matter of how many predictors we have. So there's an intercept beta 0, and then every variable xi has a certain coefficient beta I. So in this case, we have up to p variables, so up to p betas. We saw how to model nominal predictors, categorical predictors, and we introduced the concept of a dummy variable. So in this case, we have these dummy variables, z married, for instance, z divorced, which are going to represent certain deviations from a reference case. And so those dummy variables are only going to be either 0 or 1. Then we have interaction effects. For instance, we saw the interaction between how much we advertise our product on TV and radio. So we have here the main effect of the TV, the main effect of the radio, and here in beta 3, we're modeling the interaction between TV and radio. And we saw it's kind of how much they're reinforcing each other. And then we talked about transformations. There's nothing wrong with transforming our variables. So instead of fitting a model with x1, we're fitting a model with the log of x1 or with x2 squared. Nothing wrong with that. And so now we're going to start talking into the variability in all these coefficients, in all these betas. So let's see, it's about the precision of the estimates. So we see that depending on the data we use to fit the model, we are going to have slightly different estimates. The point is, how different? The issue is that normally we just have one data set. That's it. We don't have multiple data sets to fit multiple models. We just have the one. So given this one data set and our one set of estimates, well, what can we say? We only have one number, one coefficient. So what can we say about its variability? So we need a certain way to quantify the precision given just this one estimate we have. So what should we expect intuitively from this estimation? Well, first of all, it should be unit agnostic. Whether we measure our variables in grams or kilograms shouldn't make a difference. And intuitively, the more data we have, the more precise the coefficients should be, the closer they should be to the optimal values. If the data to begin with are not too much variable, they don't have a lot of variability, then the coefficients should be more precise because that means it's not so difficult to come up with a good estimate. And if we have a good data coverage, then the coefficients should also be precise because we're kind of covering the whole spectrum of possible values that we might encounter. So let's see a few examples. Let's say that in reality, the model is something like this. The response y is 2 plus 3 times x and a certain amount of variability that we don't know about. In this case, let's assume it's something like with a standard deviation of 3. So reality looks like this. Of course, we don't know in reality what it is, but just for illustration, let's assume it's something like this. And once we start collecting data, we might fit a model. So let's say that in our cases, we are looking for values of x between 0 and 5, and then we're collecting 30 observations. Each of those blue lines here represents a possible fit. So let's say we sample 30 observations with x between 0 and 5, we measure y, and then we fit the model. One line. Let's say we replicate this process and we sample a different 30 observations, we fit the model, we have another line. So you see here how much those lines differ from the true optimal model, the one in black. There's a certain amount of variability over here, right? In all these blue lines. They're still close, they're kind of on average giving us the right answer, but there's a certain amount of variation. What happens if we go from 30 observations to something larger? Let's say we go to 100. Then the thing is that, yes, the models are getting closer and closer to the optimal model, to reality in this case. So there's less variation. What happens if it turns out that in reality, there's more variation in the data? So this epsilon doesn't have a standard deviation of 3 in this case, it's something larger, something like 10. Then we see we're back to a lot of variation in the linear model. So any given data set might differ substantially from the optimal model. And what happens if instead of covering the full range of 0.5 for the predictor here, we only sample observations in a more narrow interval, something like between 2 and 3? Then, well, what's going to happen is that the model is going to be fitted only with data in around here. So it will vary a lot if we don't account for the larger scope of the variable. And so you see, these are all possible factors that are going to affect our estimates, the variability in the estimates. And of course, given that, they're going to affect our conclusions from the linear model. And so something important to note here is that everything here on the left depends on the reality under study. So these two, these three, and the amount of variability is not something that we can control. It's something about the reality we're studying. It's out of our control. There's nothing we can do about it. If there is a lot of variation, that's it. We need a lot of observations. The things on the right are things that depend on the study design. So which range of values we choose, how many observations. And everything we've seen in the lectures about methods, about sampling, about study design and everything is what plays a role here. Those are things that in principle are under our control. If we are designing the study, if we're just given the data, then sure, we don't have any control over it, but at least they should allow us to be cautious about the conclusions we draw from the model because we know there might be a lot of variability in it. And so a second thing to note here is that the precision of the estimates, of the coefficients, are going to kind of propagate into the predictions. So if we have a certain amount of variability in the model, whatever prediction we make from the model should also have a certain amount of variability. And so the prediction we make from the model is actually the expected value of the response in that point of the feature space. It's the expected value of y given that point in the space. And there's going to be certain variation in there that we will see later how to model, and it's something that we have to account for. It's not only about variation in the coefficients, it's about variation also in the response. And so unless the model is perfect, there's always going to be some kind of error. It comes from sampling, for example. And here are some questions for you. Do you think this is irreducible error or reducible error? Linking back to the lecture on models. Can we quantify this amount of error? So how can we start answering these questions? Well, by introducing assumptions into the data and the model. So the linear model tells us only about the given data, nothing else. If we want to start reasoning about populations, not just samples of data, then we introduce these assumptions and we talk about statistical models. And so what kind of assumptions do we typically impose into a linear model? Well, typically these four. First of all, we assume that the distribution of the residuals is Gaussian, so they follow a normal distribution. You know, this distribution that is kind of symmetric around, in this case, 0. We assume that the distribution of residuals is normal. We also assume that the observations are independent, that there's no relationship between one observation and the other. We assume no collinearity, meaning the predictors are uncorrelated. That's a very strong assumption in reality. And we also assume something called homoscedasticity, which means that the variance of the residuals is constant. Regardless of what kind of prediction we make, the variance in that prediction is always the same, is constant. And so it turns out that if we fit the linear model through OLS, ordinary least squares, turns out we are optimizing for certain statistical criteria that have to do precisely with these assumptions. We're not going to get into it, but it turns out that's, from a statistical point of view, also optimal in a certain sense. And so, all right, what do these assumptions tell us once we start fitting models? Well, the first thing we could do is consider standard errors, just like what we've done so far. So we shouldn't just look at our current estimate of a coefficient. We should be looking into the sampling distribution of that coefficient. So again, is the distribution that we expect for that coefficient across different samples of data. And it so happens that this is a t-distribution. We are back again to students' t-distribution. And if we have a sampling distribution, then we also have a standard error, right? So the standard deviation of this sampling distribution is the standard error of the coefficient. And everything we've seen so far about sampling distributions and standard errors and how we can use them to start quantifying this uncertainty and adjust our conclusions accordingly, same thing applies to the linear model. And so for a simple linear model of only one predictor, then here we have the equations for standard errors. And we see certain things that we've been intuitively expecting so far. It depends on the variability of the model. It depends on the amount of observations, etc., etc. And so if we have standard errors, what's the first thing we can do with them? Confidence intervals again. So once we know the standard error, we have an estimate for it, we can plug it again in this equation, and depending on the value of t, which again relates to the distribution, we may have a confidence interval. So we will say we have a certain point estimate for beta j plus minus a certain margin of error that we can compute based on the standard error. So the value of t is what's going to determine how wide or how narrow this interval is, depending on how much confidence do we want to pose into that interval. So for example, if we want a 95% confidence interval, meaning alpha is just 0.05, then we do something like t equal 1.96 or 2. So that means a 95% confidence interval for this specific coefficient is going to go twice the standard error to the left and twice the standard error to the right. And there we have an amount of variation, a quantification of how much variation is expected from this coefficient. And therefore, we provide a range of values for beta j. It's not just a single point estimate, it's a range of values. What else can we do with coefficients? Well, we could start testing hypotheses about coefficients. And again, everything we've seen so far about null hypothesis, alternative, p-values, etc. applies here. And in particular, we're always or almost always going to be interested in the hypothesis that a certain coefficient is 0 or not, because that's what makes the most sense. If a coefficient is 0, then it means this predictor is not involved into the data generating process. So that means the response is independent from this coefficient, or it doesn't help into predicting that response. And that's precisely what we want to check. Is this factor, this predictor, relevant for the response? And so we do it as always. We set a null hypothesis, H0, in which we say the coefficient equals 0, and an alternative hypothesis in which we say it's different. And so the test statistic here is again t. We are back to the student t distribution again. And so we have the coefficient, beta j, we're testing against 0, and we're dividing by the standard error. This is going to give us a t-value, a t-score. Based on that, then we can compute the p-value, and if the p-value is less than alpha, we reject the hypothesis. And so here we are again, testing hypothesis, but about specific coefficients of the linear model. And by looking into those specific coefficients, we're testing very specific hypotheses that might allow us to draw large conclusions about the different variables we're studying. But please consider everything we've talked about null hypothesis significance testing, because we know it's easy to misinterpret what it's really telling us. So please go back to the lectures on methods 3 to review everything about the hypothesis testing. Let's take a look at an example. So over here, we have the data again about advertising a certain product through the TV, through radio and newspaper. And what we saw so far is a single predictor, and we saw the regression table up to here. We only saw the estimate. That was it. So we had a certain estimate for the intercept and a certain estimate for the TV. In this case, it was about 0.05. But that was it. We couldn't say anything beyond that. Are we sure that this coefficient is positive or that it's different from 0? What are possible ranges of values? So once we start introducing these assumptions into the model and we start quantifying standard errors, confidence intervals, p-values, etc., we have a much better picture of the model. And it's going to give us the opportunity to make much better conclusions from the model. So in this case, we have, for example, a confidence interval here for the first coefficient. We see that, it's reasonably between 0.4, 0.04, 0.05, t-value, p-score, etc. Now we have a case of multiple predictors. So on top of the TV, we also account for advertising on the radio and the newspaper. And we had this funny case in which the newspaper had a negative effect. And what we saw is that, while it's not that advertising on the newspaper is going to have a negative effect on the sales, it's that once we have in the model TV and radio, then it doesn't give us too much information. And in reality, we see that it's actually linked to a very high p-value. And if we look into the confidence interval, It's telling us that, well, somewhere between negative and positive. So we don't have enough evidence in this case to say that beta 3 is different from 0. We don't have enough evidence. And so everything we could say is we need more data. There's no evidence that newspaper has a negative or positive effect. In this case, we're not sure whether it's even different from 0. And so this is something new that we are now going to be able to say about the model or about specific coefficients of the model, because we're looking into this part, the statistical part of the regression table. And now what happens when we have categorical predictors, when we have these dummy variables? Well, it's all the same. The interpretation of the coefficient doesn't change it. So in this case, we had the case of modeling the wage of an employee as a function of marital status. So we had an intercept, which was the reference, in this case, referring to never married. And then we had all these dummy variables modeling deviations from that reference. So we had something like married people. They have a salary like 26 units larger than never married. And then we had all these other coefficients for the other statuses: widow, divorced, and separated. If we look into standard errors, t-values, p-values, and everything, we notice something. For example, if we look into widowed, we see a very high p-value. This is telling us that we cannot reject the hypothesis that this beta 2 coefficient is different from 0. We see it's estimated as 6.8, but there's a lot of noise, a lot of randomness into that estimate. It varies a lot. And so we are not really sure whether this is different from 0 or not. So what we might say here is that widowed and never married, we don't know if they have a difference in salary or not. We are not certain. We don't have enough evidence for it. Maybe we need more data. For the others, we have more evidence of this difference. So again, this is something that we can only say by looking into this portion of the table. So far, we've only been looking into these estimates. Now we're able to quantify variation in the estimates and adjust our conclusions accordingly. And remember that we could also fit a model in this case without the reference case, without an intercept. And what happens is that each of those coefficients, beta 0, beta 1, beta 2, etc., they don't measure a deviation from a reference. They measure the actual average for that group. So we see that now each of these estimates is actually the estimate for the wage of those groups. They're not deviations from a reference point. And so, of course, when we do that, we expect these coefficients to be quite different from 0, because, again, they measure absolute wages. In this case, they are not measuring differences between wages. And so, of course, the p-values are all going to be, in this case, very small, because those coefficients are very different from 0. So we need to be careful when we are omitting the intercept into the interpretation of the p-values. It's not that suddenly, just by changing the model in this way, we do have statistically significant effects. No, it's exactly the same model. We're just looking at a different interpretation of the coefficients, but the model is exactly the same. Those numbers are telling us exactly the same as in the other case. And finally, let's talk about interactions. So let's say in this case, we had the salary as a function of insurance, whether a person has or not health insurance, and the job class, which could be either industrial or IT. And this coefficient, beta 3, is the one measuring the interaction. The specific case where the person doesn't have insurance and is working in IT. And what we had over here is, well, for instance, we see when a person does not have insurance, there's a negative deviation of negative 24. When a person works on IT, there's a positive deviation of 15. And by looking into the p-values, we see that we do have a good amount of evidence for these coefficients to say that they are different from 0. So there are differences in principle between insurance, yes, no, and job class, industrial, or IT. But now when we look into the coefficient beta 3, which models an interaction, we have here a negative 4 prediction or a negative 4 estimate. What the p-value is telling us is that, again, we don't have enough evidence to say that this coefficient is different from 0. So there might be an interaction, maybe not. We don't know. We don't have enough data. So we might be inclined to say that there's not enough evidence to say there is an interaction. And this is all about the coefficients. And we've seen numerical coefficients, categorical coefficients, and interactions. Our interpretations of the model might change once we start looking into the statistical part of the regression table. And what can we say about the predictions? Again, this uncertainty in the coefficients, into the betas, propagates into the response. So a predicted score, a predicted y hat, is also going to have a sampling distribution and standard error. And this is going to give us the opportunity to make predictions that account for uncertainty. We're going to be able to make, for example, interval predictions. And we have two possibilities to make those intervals. We could do a prediction interval, and those intervals are going to account for variability in individual observations. So any new observation we are able to make, then we can quantify how much variation we expect for that. And we are also going to be able to do a confidence interval, which means on average, how much variation do we expect from the model? So on average, we're going to quantify the response on the model to be around here. In a prediction interval, we are given intervals for individual observations, not averages. Let me show you an example again. So here we have the relationship between the wage of people and their age. And in this case, we have a simple linear model. Only one variable, no transformation, nothing. And here in blue, we have the point estimate. So that means just the regular point estimate we've been doing so far in a linear model. We plug the values of the variables into the coefficients, we sum, and then we have an estimate for y. That's it. Now that we start introducing these statistical assumptions, we can have prediction intervals. And in this case, this one here is a 95 prediction interval, and this one here is a 99% prediction interval. What this tells us is any given observation, any given new observation, is expected to come around this interval 95% of the times or 99% of the times. Again, technically speaking, it's not really that interpretation, it's rather how many intervals would contain this fraction of predictions, but let's not get into there. And so what this shows us is that, yes, the prediction is going to be there, for example, at this value of the age, but any given observation is actually expected to vary this much, 95% of the cases, or this much, 99% of the cases. When we look into the confidence interval, what we're given is an error bar or a band of confidence around the average of the model. So what this is telling us is that the model, if we start looking into this variability across different training data, is going to vary so much on average. So of course, there's a lot less variation when we talk about just the mean, just a little bit. Any given observation may vary a lot, but the mean is not expected to vary that much. And the same happens if we have, by the way, transformations. So in this case, we have a quadratic relationship between the age and the wage. No problem. Those intervals are just going to follow that transformation. And so again, for a point estimate over here, we're now able to quantify a prediction interval, 95%, and we're also going to be able to quantify over here on average. So again, the difference between a prediction interval and a confidence interval is that in the prediction interval, we give an interval for the expected variation in an individual observation, one individual prediction. In the confidence interval, we have the expected variation on average for all given observations and different data into a point like h equals 70 in this case. So if we are using the model to make predictions, now we're able to attach to our prediction a certain amount of variability. And maybe given that variability, we might be inclined to make one decision or the other, or no decision at all.